Welcome students to this video lecture on chemistry. Now this is a big chapter and a lot to cover, and we're going to break this video lecture into two parts. So let's jump right into it here. Let's take a look at our objectives for this video lecture here. We're going to be able to define, describe matter and elements, identify and describe atoms and their structure, identify and describe chemical bonding, compare and contrast organic versus inorganic molecules, including talking about pH, and then we're going to define in detail the role of organic compounds. So let's get into it. The heart of chemistry really revolves around this idea of matter. Now, matter is anything that has mass and occupies space. Pretty vague sort of statement there, but that's what matter is. And so anything that has mass and occupies space, whether it's a tiny amount of space and a tiny amount of weight or mass, it's considered matter. Now there's three states of matter: solid, liquid, and gas. Now I'm sure you can all sort of relate. If you think of water, it can be solid, as in an ice. It can be liquid, as in what we drink. And then it can be a gas state where when you boil water, the gas vapors sort of evaporate into the atmosphere, into the air. And so you can think of other gases. Carbon dioxide is a gas. Other liquids could be, geez, anything really. Look in your fridge. Milk, can be considered a liquid. A solid, then, the table, the chair that you're sitting at, and the table that you're with, that can be a solid. The composition of matter. So what is matter made up of? All right, so, you think of water, you think of milk, you think of this chair you're sitting in. That's all matter. And what is matter made up of? Matter is made up of these things called elements. And elements cannot be broken down by ordinary chemical means. They're the sort of most basic sort of structure in chemistry that we have. And each element has its unique properties. There's physical properties and chemical properties. Physical properties are detectable with our senses or what we can measure. The chemical properties are how atoms interact, bond with one another. So we'll get to this idea or this concept of atoms, but one thing to understand, that matter is anything that takes up space or has mass and occupies space. And matter is made up of elements, or a element, okay? Matter can be just one element or a combination of elements. So what are these elements? Now again, as I said, an element is the simplest form of matter to have unique chemical properties, okay? It's the most basic sort of thing within matter. And each element is composed of protons, neutrons, and electrons. Okay, so basically each element is composed of these items called atoms, or a structure called atoms. Okay, and so it's breaking down. We're breaking it down. So matter is anything that has mass and occupies space, and matter is composed of elements, and then elements are composed of these particles called protons, neutrons, and electrons. And an element basically is an atom. So an atom is made up of protons, neutrons, and electrons. And the atomic number is, each element is identified by this number. It's the number of protons found in the nucleus, and it's how the periodic table is organized. Now I know I'm throwing a lot out there right now, but we'll get into each one of these details in a little bit here. So again, elements are composed of protons, neutrons, and electrons, which are referred to as atoms. So atoms are the unique building blocks for each element. Okay? So the atomic symbol, the 1 or 2 letter chemical shorthand symbol for each element that you find in the periodic table, refers to a specific element, but also refers to a specific atom. So here's the periodic table of elements, okay? If you look up here, we have hydrogen, it goes helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, okay? These are arranged, the atomic, or the periodic table is arranged in the atomic number. And again, the atomic number is referring to the number of protons within the nucleus of a atom. And I know this is probably confusing, but bear with me. We'll kind of wrap this all together here, okay? So hydrogen is an element. Helium is an element, okay? Think of water, H2O, if you write it out in that sort of format, that means 2 hydrogen atoms and then 1 oxygen atom. So water is composed of the element oxygen and hydrogen. Now, oxygen is an element with an atomic number of 8, which means that there is 8 protons in its nucleus, and helium is an atom or is an element with the atomic number of 1. So this atom has only 1 proton within its nucleus. So let's jump into this sort of idea a bit more, and then we'll get into it in more detail here too. So if we look here, the atomic number, okay, so all these elements, let me back up, all these elements are made up of atoms, okay? Boron is made up of atoms, carbon is made up of atoms, but there's carbon atoms, there's nitrogen atoms, there's oxygen atoms, there's fluorine atoms, okay? And then there's iodine atoms and so forth. But atoms, as we said, are composed of protons, neutrons, and electrons. And what makes a carbon atom carbon atom, and what makes a nitrogen atom is the number of protons that that specific atom has. Okay, so you have 6 protons in carbon, 7 protons in the atom of nitrogen. Okay, so let's kind of take a break from that and get into this idea. There's 91 naturally occurring elements on Earth. Okay, and as I said before, the periodic table lists them in the atomic number, which is the number of protons in the nucleus of that atom. 24 of them play a huge, 24 elements that is, play a huge physiological role within our body. And 6 of them account for almost 99% of our body's weight. So about 98.5% of our body's weight is made up of oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus. Okay, and then we have some trace elements and minerals that round out the other 1.5%. As I said, water is composed of 2 elements, oxygen and hydrogen. So there's an oxygen atom, and then there's 2 hydrogen atoms. So about 96% of our body's mass is oxygen, carbon, hydrogen, and nitrogen. Okay, so if you take those elements and you extract them from our body, that's about 96% of our body mass. It's pretty amazing to think. The rest is calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium, iodine, and iron. Okay, so there's about 4% of our body mass is made up of those elements. And trace elements are chromium, magnesium, and zinc. That's not important that you know this specifically. What we want to study now is the atomic structure. So as I said, and as we've been looking at, each element is made up of a specific atom. And that atom is defined by the number of protons it has within its nucleus. And so you're probably sitting there saying, what the heck is a nucleus? Well, the atomic structure is the sort of structure an atom will take. And it has like 2 major components to it. It has a nucleus and then what we call an electron shell. The nucleus contains protons and neutrons. And then the electron shells are where obviously the electrons are found. And we have the shells, and we'll talk about those in a second here. I want to give a picture here first, okay? So I'll go back to those slides in a moment, but here is a sort of a specific view of a carbon atom right here. And this carbon atom has an atomic number of 6, which means that there is 6 protons within the nucleus here. So here's the nucleus of this particular atom. Here's the nucleus of this atom, which is nitrogen. Here's sodium. Here's the nucleus of sodium. And then here's the nucleus of potassium. Now, each nucleus will contain protons and neutrons. What sort of surrounds and wraps around the nucleus is what we call the electron shells. Now the electron shells, as we said, are where the electrons are found. And there can be up to, I think it's 7 shells that wrap around a particular nucleus, okay? And so typically a neutral atom where it has no charge contains the same, a general rule of thumb, each atom contains the same number of protons as it does neutrons, as it does electrons. Okay, so if this has an atomic mass of 6, which means that there's 6 neutrons or 6 protons in the nucleus, that means that there's 6 neutrons in the nucleus too, and that there is 6 electrons. So we have 1, 2, 3, 4, 5, and 6. Same with here. We have an atomic mass of 11. That means 11 protons in the nucleus. 11 typically means 11 neutrons in the nucleus too, but in this case we have 12 neutrons. Okay, that's what is normal for the sodium atom. Okay, but rule of thumb, as you can see here, 7 protons, 7 neutrons. Okay, it's not that you have to ever memorize, you know, that sodium has this or that. Okay, the thing that we want to really focus on is the number of protons, and because that determines the atom. If an atom has 11 protons in the nucleus, that means it's sodium. If it has 7 protons in the nucleus, it's nitrogen. If it has 6 protons, that means it is carbon. Okay. Now the number of electrons usually balances out with the number of protons. So we're going to have 11 protons here, and we're going to have 11 electrons. So 1, 2, and 3, 4, 5, 6, 7, 8, 9, 10, and then 11. Okay. So these electrons are arranged in a particular order. Okay, and that order is referred to as the electron shells. The first shell can hold up to 2 electrons. Okay, so the first shell around the nucleus can hold up to 2 electrons. The second shell can hold up to 8 electrons. The third shell can go up to 8, and so forth. Okay, 8 is kind of that magic number. Each electron shell after the first one wants to get 8 electrons. That is stable. Okay, so when we look at this chart here again, we have in carbon we have 6 protons, so we're going to have 6 electrons. And the first shell here, here's the first shell, has 2. That's all it can hold. It's happy with 2. The second shell, though, has 1, 2, 3, 4. Now it's not that happy of a camper. It wants 4 more electrons to be really happy. Okay, it's kind of like that in between sort of one. But if we look at sodium here, it has 11 protons, and we already went through it, has 11 electrons, has 2 in the first shell. Here's the first shell. Here's the second shell. Here's the third shell. Okay, so 1, 2, the first electron shell is filled. In the second shell, it can hold up to 8. 1, 2, 3, 4, 5, 6, 7, 8. Beautiful. It has 8. It's happy with that. But in the third shell, it only has this 1 electron. So here's the deal with sodium. And what we're going to look at when we talk about bonding between atoms is that electron in that outer shell, it either has to gain 7 electrons to get to that 8 of the outer electron shell being stable, or if it could give this 1 electron away to another atom, right? If it could give that electron away to another atom, it would then have 8 in its outer electron shell, and it would be stable, and it would be very, very, very happy, okay? And so we'll come back to that when we talk about bonding, but I want to finish this talk out here, okay? So the big thing about the valence shell is the outermost shell, the last shell out there. So we're looking here, this is the valence shell, 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 okay? These are all electron shells. First one, all these can only hold 2. And then the shells from out there, second, third, fourth, fifth, sixth, seventh, can hold up to 8 electrons. And it wants to hold 8. It's not going to fill this second shell with 5 and then this one with 12 or 11, I should say. Okay, it's not going to do that. It's going to hold up to 8 and then it's going to go out to another shell. And this is probably still kind of like, oh, what's going on? But that's fine as long as you're kind of somewhat following around. So what we got is the electron shells. The outer shell is called the valence electron shell. And then what we want to do is get that to be filled with 8 electrons. And again, that's going to ultimately determine the chemical bonding property of that atom. So how does one atom interact with another one to make a sort of a molecule or compound is going to be determined by the electrons. Okay. Again, the big thing though is the protons. The number of protons in the number of protons in the atom determine the element. Okay. And so when we talk about atomic weight, it's the weight of the protons and neutrons. Usually, general rule of thumb, most elements roughly have the same number of neutrons and protons. Okay, we saw that there is a slight difference in some cases. But protons have 1 atomic mass unit, AMU. Neutrons do 2. Electrons are so small that we don't weigh them in. So when you see atomic weight, it's the weight of the protons and neutrons. Okay, so what we have, you can look at the atom in a couple different sort of models. We can look at a planetary, which we were just a moment ago, or an orbital model. Okay, and there's a little difference between these two, but I want to say this is the planetary model, so this is not technically, when you think of an atom, you can think of it this way, but here is a good example between the planetary and the orbital model. Okay, so the electrons just don't kind of circle around. They form this sort of cloud, so to say. And we're not going to get into that much detail. This is really advanced stuff. But I want you to understand the nucleus, protons, electrons. The protons determine the atomic number, okay, and they determine the sort of type of element it is. Now, the electrons, here's one electron shell. The first electron shell wants to be filled with 2. Boom. Helium's happy with 2, okay? So it has 2 protons, 2 neutrons, 2 electrons. The atomic weight would be 2 plus 2, which would be 4. The atomic number is 2 because the atomic number is the number of protons in the nucleus. Okay. Identifying elements. We've been talking about this. Atoms of different elements contain different number of subatomic particles. So we're going to compare hydrogen, helium, and lithium. So hydrogen has 1 proton, no neutrons, and 1 electron. Okay, but this electron shell, the first one, wants to have what? 2. So it's going to be looking for a partner at some point. Now, helium has 2 protons, 2 neutrons, and 2 electrons. Okay, lithium has 3 protons, 4 neutrons, okay, and then 3 electrons. All right, so that's how we kind of look at those. And again, identifying these elements, we have the atomic number, which is the number of protons in the nucleus. The mass number is the atomic weight, which is the mass of the protons and neutrons. And again, the mass numbers of atoms of an element are not all identical. We can have these things called isotopes, and we'll talk about that. So, and again, this is a little more advanced for what we're going to be getting into. So you can have, the atomic weight is really the average mass of all its isotopes. So we can have hydrogen. Normally hydrogen has 0 neutrons, but we can find it with 1 neutron or 2 neutrons, okay? It still has 1 proton, because if the number of protons changed, the element would change itself, okay? So this has 2 neutrons, this one has 1 neutron. It's still hydrogen in that sense, but it's got a little different name with that. So that's the idea of isotopes. They differ in the number of neutrons. Extra neutrons increase the atomic weight, okay? So they have, everything else is the same except for the neutrons. There may be more or less neutrons. And again, the atomic weight is that atomic mass average of the isotopes. Now, radioisotopes are something that you see in healthcare quite a bit. So certain isotopes are unstable, and these are called radioisotopes. They're unstable isotopes of a certain element. And they'll break down into a stable sort of form of that element, but when they break down, they decay and give off what we call radiation. So radioactivity is the process of decay of radioisotopes into stable isotopes. Now here's the thing, is that as these radioisotopes break down into that stable form, it may take a short time, a couple minutes, for it to actually occur, a couple hours, or billions of years in some cases, okay? So the radioisotopes, they spontaneously break down, they spontaneously decay. It doesn't take any sort of effort for them to do that. And the energy they give off is called radioactivity. And so these sort of, or the energy, the radiation it gives off can be detected with scanners. And so we've used these radioisotopes within certain scans that we can, inject an individual with a radioisotope, and like for example, iodine, radioactive iodine, a radioisotope of iodine is used to treat thyroid cancer. And iodine goes to the thyroid, and that sort of breakdown of that radioisotope will damage the thyroid, killing the thyroid and basically killing the cancer. And so there's all sorts of different things that these radioisotopes can be used for. I shouldn't say used for, but in healthcare they can be used for various different things. But not all of them are safe to be able to use. You think of the sort of nuclear power plants and the radioactivity. Those are radioisotopes that are breaking down. They take a long time to break down, and they give off a lot of radiation, and that radiation can cause, even cause cancers or cause various different complications. Okay, before we jump in there, I want to go back to the periodic table just to kind of wrap things up again. Okay, so when we talk about chemistry, we're talking about the idea of matter. And matter is anything that has mass and takes up space. Even if it's a tiny, small amount of mass and a tiny bit of space, it's still considered matter. And matter is composed of elements. And elements are made up of atoms. And not just any atoms, but there's specific atoms that make up each element. Okay? And so here's the periodic table. And we're looking at, let me see if I can find it here quick. Where'd it go? Oh, right here, sorry. Gold, AU. So the atomic lettering for gold is AU, okay? So when you see AU, that's referring to gold. HG is referring to mercury, okay? Now gold has an atomic number of 79. We know that means what? Okay, you should know that 79 is referring to the number of protons in that atom. So gold is made up of specific atoms, and these atoms will have 79 protons in the nucleus. Okay? Now silver, right above it here, has 47, atomic number 47. That means that there's 47 protons in silver, and compared to gold, which has 79. Okay, so there's 79 protons, 47 protons in the nucleus in these two. Now, is it easy to convert one element to another? No, it's not. Otherwise, we would be all kind of rich because we'd all have gold. And actually, we wouldn't be rich because gold wouldn't be worth anything because we'd be able to make gold from almost anything. So if we had, let's say, chlorine or sodium, right, 19 or 17 protons in the nucleus, can we, I'm sorry, not, that's potassium, 11 or 17, we would have to do a lot of work to get it to be 79 protons in there. Same with silver. You can't make silver into gold. And the reason is because silver is made up of the specific atom that has 47 protons in the nucleus, where gold has 79. So you can't change the number of protons in the nucleus very easily. And in fact, it's very, very difficult process, and we can't do that in a lot of cases. We can, and I don't want to get into the nuclear process of fission and fusion, but this is something that can't be done. Now we can change the neutrons in here, the amount of neutrons in this nucleus, and we can change the electrons a bit, but to change the proton means that you're changing the element. So you're going to be taking oxygen if you have 8 protons in the nucleus, and you take one out somehow. If you could take one, if you have an atom of oxygen or atoms of oxygen, and you take out 1 proton from the nucleus, and there's 7 in there, then you have nitrogen. That just does not happen. It's very, 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 very uncommon for that sort of stuff to happen. So what this means is that each element is made up of a specific atom. There's oxygen atoms, there's fluorine atoms. Okay, and how do we determine the difference between these two atoms? Is the number of protons in the nucleus. Okay, so that should help you get that sort of understanding. The other thing then to brush upon that I just went over is protons have a positive charge and neutrons have a negative charge. I shouldn't say negative, but neutral charge. So protons carry a positive charge, electrons carry a negative charge. Okay, so if we have 6 protons, I'm going to go to the sodium. If we have 11 protons in sodium in the nucleus, that means we're going to have 11 electrons. Okay, if, as we said, if this electron kind of goes off to a different one, that means there's only going to be how many? 10 electrons, 2 in the first shell, 8 in the second. So if electrons are negative, we have then 10 subatomic particles with a negative charge, and we'll have 11 with a positive charge. Okay? So that would mean then the overall, if this electron went somewhere else, went to a different atom to complete a valence shell of 8 in a different atom, that would leave us with 10 electrons and 11 protons still. Protons are positive charged, electrons are negatively charged. Overall, then this atom here would have a 1 plus charge, right? Because the 10 electrons would only balance out 10 protons, which would leave 1 proton or 1 positively charged molecule, a subatomic molecule left. So if 2 electrons left, that would mean, there's only 9 and 11 here. That would be a positive or plus 2 charge. If this atom gained, let's say it was 11, 11, and it gained 1 electron, then it would have 12 negatively charged particles and only 11 positively charged particles. That means this would have a negative 1 charge to it. Okay, and this will make sense when we get into the bonding process. So, molecules and compounds. Most atoms combine chemically with other atoms to form molecules and compounds. So we can take, for example, water. It's combining 2 hydrogen atoms with 1 oxygen atom to form a compound. So what's the difference between molecule and compound? Well, really not all that much. A molecule is 2 or more atoms bonded together. Okay, so if we have H2, that's 2 hydrogen atoms bonded together, or C6H12O6, obviously that's 2 or more atoms bonded together. Now a compound is slightly different. It's 2 or more atoms bonded together, but they're different. There has to be different kinds. So like C6H12O6, that's a compound because there's 2 or more different types of atoms. Or you can even think of it as elements, but 2 or more different types of atoms. H2 is not a compound, even though there's 2 or more atoms bounded together, but there's not 2 or different kinds. So it's, it's kind of like that. It's a thin difference between the two. Okay, so when we get these, when we talk about matter, most matter exists as mixtures. Okay, so right, you think, you don't have like a chair completely made of carbon. You don't have a chair completely made of gold or anything like that. Most matter that we see, whether it's the matter comes in the forms of gas, solid, or liquid, is a mixture of various different elements. And so there's 3 types of mixtures. There's solutions, there's colloids, and then there's suspensions. So solutions are homogeneous mixtures, usually transparent, meaning you can see through it. An example is atmospheric air. Our air, obviously we can see through that. That's a mixture of various different gases. Seawater is water mixed with sea salt, which is salt basically, and that is transparent too. So when we have a solution, we have two things. We have a solvent and a solute. The solvent is present in the greatest amount. It's usually the liquid. So if we think of salt water, right? The solvent would be water. The solute would be salt. The salt mixed in there. So think of Kool-Aid, okay? So Kool-Aid's a sort of mixture. It's a solution. It's composed of sugar and water and a little food coloring, but we'll just say sugar and water, right? And so the solvent there again would be the water, and the solute would be the sugar. So the concentration of solutions are expressed in various different formats. It could be percentage-wise, it can be milligrams per deciliter is a common way of expressing it in a scientific or medical format. Like sugar in our blood. Let's say, someone measures the sugar in the glucose, the blood sugar levels, and they'll measure it in milligrams per deciliter. Milligrams is an amount, like a weight, and deciliter is a volume. Okay, and then also you could see it weighed in as molarity or moles per liter. And I do not want to get into that with you guys because that's some deep chemistry. Not deep chemistry, but I don't want to go over your heads all that much. And that's not really going to affect us in our sort of scope of practice that we're looking at in chemistry. This is just 1 week of chemistry that we're doing. But we'll use stuff in lab as milligrams per deciliter, and you'll see percentage. Is like form a 8% solution of sugar water or salt water, okay? So that means 8% of that solution is sugar or salt, whatever you may be using. Now, colloids and suspensions. Colloids are emulsions, and they're heterogeneous, which means that they're a mixture of things. And so these usually contain large solute particles that do not settle out. Okay. Suspensions then are also heterogeneous mixtures like blood, and they're large visible solutes that tend to settle out. Okay, so we got ones that do settle out, and we got ones that the solute particles that do not settle out. Okay, again, the solute is that sort of whatever's presented in a smaller amount. Okay, so we talked about salt water, the salt was that. So in a colloid, or colloid, what we have is, and they do not settle out. In suspensions, they tend to settle out. So here's a good sort of diagram to depict it, or depiction of the differences between solution, colloid, and suspension. So solution here, we have mineral water, which has various different sort of minerals, carbon, stuff like calcium, phosphorus, and sodium within it. And the solute particles are very tiny. They do not settle out or scatter light. So they basically dissolve in that sort of solution almost. A colloid is, you think of like gelatin with particles floating in it. Okay, so they do not settle out of there, where in blood they do, and that's a suspension. So the solute particles are very large, they settle out, and may even scatter light. So when you spin the blood down, you can see the difference between, you can see the particles and that sort of thing. So we're not really going to spend much detail on this through our week either, but just so you're aware of the difference between a suspension, colloid, and solution. Now, mixtures versus compounds. Mixtures, there's no chemical bonding between the components, can be separated physically by straining or filtering. Okay, so it's like mixing rocks with water or sugar with water. Sugar is not really the best example there, but a mixture is like you combine two things, kind of like think of water and oil. You mix them together, and then they can separate out physically The oil actually sits on top of the water. Compounds, what we can see is the compounds can only be separated only by breaking the bonds. So there's the bonds between the two different sort of components or various components going in there. The bonds are actually being broke there. So these are just general sort of definition ideas. But here's a big concept that we want to sort of really kind of wrap our minds around is chemical bonding or chemical bonds. So again, the electrons occupy up to 7 electron shells, okay, around the nucleus. So the first one, it wants to fit 2, and then the second, third, and fourth fit 6, up to 7 electron shells out want to fit up to 8, and that's called the octet rule, where they want to have 8 electrons in that outermost shell, and that's again called the valence shell. And so that outer shell, how many electrons are in there, really going to determine the chemical bonding properties of that atom. Okay, and what we'll see some examples of that. So chemically inert elements are stable and relatively unreactive. That means because of their outer electron shell, their valence shell is usually occupied with 8 electrons. Or if it's the first electron shell, it's filled with 2. So if we look at chemically inert elements, that means that they're not really going to be chemically reactive with other sort of molecules. So helium has 2 protons, 2 neutrons in the nucleus, and 2 electrons in its first valence shell. That means it's complete. Neon is another example, 10 protons, and it's going to have 10 electrons, 2 in its first shell, and then 8 in the second one. So this is happy. It's very happy with that sort of arrangement of its electrons and protons, and it's going to stay like that. Neon, you can't really get to chemically bond with other sort of elements because of the stability that it has in its valence shells, and same with helium. Chemically reactive elements, though, that means the valence shell, the outer shell of electrons, are not completely filled, and they will either gain, lose, or share electrons to form bonds with other atoms to achieve this stability. Now, this is pretty cool stuff. So you think of hydrogen, it has in its 1 electron shell, its first electron shell, it has 1 electron. It wants another one to complete 2. Carbon, 2 in its first one, cool. 4 in the second one, it wants 8. It's kind of in between. Is it going to lose those 4 or is it going to gain 4? Okay, so we'll see what happens to carbon. Sodium has 11 protons, and that means 11 electrons. And so 2 in its first one, and we looked at this one before, 8 in its second one for 10, and it has this lonely one out here, and so that means it's probably going to leave to some other electron. Oxygen, 2 in its first one, 6 in its second one, so it has 2 gaps to fill in its outer electron to achieve 8. So it wants an electron shell to achieve 8. So it wants to get to that balance there. And so there's 3 types of chemical bonds that will occur to help achieve this outer valence shell to get 8, or in this case, in the first shell, to achieve 2. There's ionic, covalent, and hydrogen bonds. Okay, so these are the 3 different types of chemical bonds that will work with atoms, one atom will combine with another atom to get to that 8. All right, so ionic bonds are formed by the transfer of valence shell electrons between various atoms. So anions have gained 1 or more electrons. That means they gained a negative charge. Cations have a positive charge. They lose 1 or more electrons. Okay, so then the attraction of the opposite charges result in an ionic bond, right? Negative and positive tend to attract. Opposites attract, right? So here's a great common example. Sodium and chlorine to form sodium chloride, otherwise known as salt. All right, so we have sodium. Again, we had this lone ranger out here in its outer valence shell. It has 1 electron out there. Then we have chlorine, which has 17 protons, 17 electrons. All right, let's see how that works. First one obviously filled. The second shell, two 2 here, 2 here, that's 4, 6, 8. Its second shell is happy. Its third shell is 2, 4, 6, and then 7. It wants 1 electron. And so what atom has 1 electron to give? Sodium. Boom. So what happens? Sodium pretty much donates this electron to here to complete 8 valence electron, or 8 electrons in the valence shell of chlorine, and then we have 8, because this atom's gone, we have 2, 4, 6, 8 here. Wicked, right? That's pretty nice. So this then has a positive charge. This then will have a negative charge. It picked up 1 negative electron and it lost 1 negative electron, so it leads to a positive negative. And so that's what happens. Ionic bonds then are transferring of electrons from one valence shell to another. And when this happens, you form ions, positive and negative ions, and these ions tend to attract to one another. They like to be held together, right? Opposites attract. So in this case, the positive and negative kind of holds those two atoms together. Okay. Now, this bond is not that strong, okay, because if we add sodium chloride, salt, table salt, to water, what happens? Well, the water breaks up the bond between the positive and negative charge, and what you end up in solution is sodium with sodium atoms with a positive charge, and then chlorine atoms with a negative charge. They're separate, okay? Otherwise, they're bonded together by that negative charge, but when you put them in water, water easily breaks that weak bond and separates them into the various different ion charges, okay? So that's where the ionic comes from, because it forms these ions. So ionic compounds form crystals instead of individual molecules like sodium chloride, right? You think of salt as a crystal, okay? And you can see here they form these sort of crystals, like just the way they're attracted to one another. But again, they're a weak bond, so when you add them to water, water will even break up those sort of that attraction between positive and negative ions to separate into their specific ions, sodium and chlorine or chloride. Now, covalent bonds formed by sharing 2 or more valence electron shell electrons. Getting these electron valence shell sort of thing jambled in my mouth, but I think we get the point. So instead of donating or giving away 1 or 2 electrons from one valence shell to another, covalent bonds tend to share the electrons. Okay, it allows for each atom to fill its valence shell at least part of the time. And so this bond is pretty powerful because what we have here is hydrogen and carbon, right? Carbon, its outer valence shell has 1, 2, 3, 4 right here, and it wants to get to what? 4 more, so it wants 8 total, so it needs 4. Hydrogen here is missing 1, okay, in its first, or in its valence shell. The first valence shell wants 2, so it's missing 1 in each one. So what happens is usually you get excuse me, methane gas formed if carbon is near hydrogen, because the atoms in the valence shell will share with one another. So look at, we have here, here, and here. They share these electrons. So carbon shares its 4 valence electron shells. Hydrogen will share its 1 valence electron shell. So we have in this outer valence shell of carbon, we have 1, 2, 3, 4, 5, 6, 7, 8. In the hydrogen, we have them 1, 2, 1, 2, 1, 2, 1, 2. So they kind of share. They go, oh, I'm going to go over here, I'll go over here, I'll go over here, I'll go over here, something like that, right? But there is that sharing of the valence electron shells. Now, this bond is very, very strong because they're sharing the electrons, and so they don't want to break apart because they'll break apart into a unstable valence, outer valence shell amount of electrons. So covalent bonds are very, very strong. Again, what we have here, oxygen is another common. So atmospheric oxygen is O2. It's just not oxygen molecules. They're bonded together, really. Because why? We have 2, 4, 6, okay? And we're missing 2. And so 2, 4, 6 here, and we're missing some. So they form a double bond. So they share 2 electrons. 2 groups of electrons, right? Because we need 8, so we got 1, 2, 3, 4, 5, 6, and then 7, 8, and same with there. So they form a double bond because they share 2 electrons, or 2 oxygen atoms share 2 electron pairs. That means a double bond. So if you see this, that means there's a double bond. It's a double covalent bond. All right. Again, in this case, we got nitrogen, and that forms a triple bond because they're sharing 3 pairs of electrons. Okay. So covalent bonds are sharing of electrons, which not is always as equal as we may think. There may be unequal sharing, which creates this sort of polarity to them. So carbon dioxide, the oxygen or the gas that we breathe out and we produce in cellular respiration. The bonds are nonpolar. That means there's fair sharing between the oxygen and carbon atoms here of the sharing of the electrons. Now, when there's unequal sharing by the atoms, what happens is we produce these polar molecules, and these are important because this is important to talk about with hydrogen bonding. But we have polar molecules that are formed. Water is a prime example. So we have water, which is H2O, 1 oxygen, which has 6, and then it needs, again, 2 electrons in the outer valence shell to complete 8, and hydrogen needs 1 in each one of those, and so that's how we have the sharing. But more of the electrons that are shared, these 2 electrons that are shared by hydrogen, are more kind of geared towards this end, or the oxygen end. Oxygen kind of hoards them a bit more because it has more negative or positive charge that pulls them in a bit more. And so what we have with with water is we have kind of a negative end and then a positive end. It's slightly polar because of the way the oxygen, or I should say the way the electrons in the valence shell are shared. It produces that slightly polar thing there. So we can have some ideas. We can have ionic bonding, which is transferring of electrons. We have polar covalent bonding, which means that there's a polarity to them. So there's unequal sharing of the electrons. They still share them, but there's unequal sharing. And then we have nonpolar covalent bonding, and that's equal sharing. So the way I describe this is, let's say it's a good example is like I have a peanut butter and jelly sandwich, okay? And I give you my peanut butter and jelly sandwich. What type of bonding is that? If I just give you my peanut butter and jelly sandwich, that would be ionic bonding, okay? If I just give you that, I transfer it to you. But if I share my peanut butter and jelly sandwich, then I cut it right down the middle, right? And give you an equal half. That would be nonpolar. I'm sharing the equal half of my peanut butter and jelly sandwich with you. If I cut it, let's say, into my favor where I want it more, and let's say I cut it so it's 2 unequal halves and I take the bigger half, that would be polar covalent. It's an unequal sharing of those electrons. In that case, that peanut butter and jelly sandwich. Now the last type of bonding is hydrogen bonding. And this is the attractive force between electropositive hydrogen atoms of one molecule and an electronegative atom of another molecule. It's kind of cool. So water forms these hydrogen bonds. DNA forms hydrogen bonds. But this is how it works. Is you have to have this polar covalent bonding. So we have negative, positive here, okay? We have positive, negative, okay? Positive, positive, okay? Positive relating to this, negative here, positive here, okay? So this is almost not like ionic bonding, because ionic bonding is much stronger than this, but there is a slight attraction between this polarity difference here, right? So we said the hydrogen or the hydrogen atoms will spend more time with the oxygen, producing a more negative charge, but then that leaves a positive, slightly positive charge to hydrogen atoms, and so this negative and positive is going to kind of attract one another. So we have this hydrogen bonding, this kind of weak bonding. And this is what we can, when you think of insects walking on water and sort of other things like that, that's due to hydrogen bonding that allows for that sort of process to occur. Now, chemical reactions, okay, so that's chemical bonding. And chemical reactions occur when chemical bonds are formed. So it takes a chemical reaction to make chemical bonding. And so things are rearranged or broken down, and we usually represent them as chemical equations. And I'm not going to get into that because we're not looking at that much detail in our week's worth of material. But the chemical reactions are either exergonic or enderonic. Geez, I can't talk. Exergonic or endergonic, sorry. Exergonic reactions release energy. Endergonic are ones that need energy to allow for that reaction to occur. So when you see these terms with chemical reactions, some chemical reactions will release, they'll just spontaneously go through that chemical reaction and release energy. Other reactions need a little energy put into them for them to occur. Okay, and so usually what you see is, a molecule A plus molecule B will form molecule AB. AB then can be broken down into A plus B again. Okay, so usually most of them are reversible, but not always the case, and I'm not going to get into that much more detail with this. But the idea with chemical reactions, for chemical bonding to occur and chemical reactions to occur, there is a specific influence, or there's various influences that can affect the rate of that reaction. And we'll talk about catalysts or enzymes later on in this lecture, but a catalyst will increase the rate without being chemically changed. And so protein enzymes are biological catalysts, and we'll talk about that later. But other things that can affect the rate of a reaction is if you increase the temperature, you'll increase the rate. If you decrease the particle size, so if you're not messing around with huge particles, you'll also then increase the rate. And the concentration, if you increase the concentration of the chemicals that are in the reaction, you will also increase the rate. Okay, so keep that in mind with chemical reactions then too. So energy, and this is just a quick sort of side note before we get to the second half of our lecture, but energy is the capacity to do work or put matter into motion. So there's two types of energy. There's kinetic and potential. And when we talk about potential energy, this is stored energy within chemical bonds. So there's a molecule called ATP in our body, which is our sort of energy source, and it has this potential energy stored within its chemical bond. So once it's broken down, once we break down this molecule called ATP, it releases energy and allows us to do various different work, like causing muscles to contract and allowing us to move. Kinetic energy is energy in action. It's actually occurring. It's boom, energy. It's not stored. It's actually energy that's occurring at the moment here. Okay, so there's those two forms of energy. And we can also, well, I shouldn't say there's just two forms. There's two types of energy, but there's various forms. There's chemical energy, as I mentioned, which is stored in chemical bonds. There's electrical energy, which is the movement of charged particles, ions. Mechanical energy, which is like muscle movement. And electromagnetic energy, which is like ultraviolet, X-rays, visible light, radiation sort of stuff. Okay, so there's various forms of energy, but they're going to fall into kinetic or potential energy. And energy may be converted from one form to another, may go from electrical to chemical or mechanical to electrical, but what happens is a lot of that energy is lost as heat. Think of like a car, right? If we could convert the gasoline that we put in a car better to allow for mechanical energy, then we would get better miles per gallon, right? So we have this sort of chemical energy found in the gasoline, and we want to convert it into mechanical energy so we can move the tires of our car, which will allow us to move. But a lot of that process is not very efficient, and we lose a lot of that as heat. And that's why your car heats up within the engine, because it's, that energy conversion is losing heat. Okay, so this is the end of the first part of the video lecture for chemistry. I kind of went through it quickly. It's a good sort of general knowledge to have, but if you take anything away, watch the second part of this video lecture, because we're going to talk about inorganic and organic compounds, and this is going to be more relatable to the material that we're covering this week in lab, and also then in the future sort of video lectures that we have, especially with the organic compounds. These are really, really important aspects and concepts to be able to retain from here on out. So the second half of the video lecture, we'll talk about these two different compounds and get into each compound type very sort of specifically.